Welcome back, everybody. So hopefully everyone has been working on their exam redo. If you have any questions on it, please feel free to remember you can email me or come to my office hours. The last office hours that are available are this this Tuesday. So tomorrow between 10 a.m. and 12:20. But if that doesn't work for you, send me an email with some times that work with you, and we can try and get something set up. What's the word? I noticed that we're not wearing our jerseys today. We should all you guys have Seahawks jerseys, correct? But you should be wearing them. Monday Night Footballs. So it is requirement. Exactly right. Danny's exactly right. It's a requirement. So next time there's a Monday Night Football game with the Seahawks, which there won't be. Next time there's a Monday Night Football game, please make sure you bring your jerseys. It's important. Okay. So we left off last time with 2.2, and we were talking about horizontal tangent lines. And the fact is, the horizontal tangent line is where the derivative would be 0. So we set that equal to 0 and find those values. And then we found that, or wait, no, never mind. We way past that. I don't know why I was still there. We talked about product rule and quotient rule. And then we had done this problem right here, which was appealing straight to the definition. So it said, find the derivative of f divided by g at x equals 1. That bar and then the x equals 1. Some textbooks might draw this instead, by the way, just so you're clear, just so that it's clear. Some textbooks might draw a line and then they just might write 1 instead of x equals 1 if they think it is assumed from the context that that's what that means. But I will always write an x equals 1 just to be very, very particular. So appealing straight to the definition, then we had to look at the graphs and the chart to figure things out. So then there's another one that says find the equation of the line tangent to the curve y equals f plus g at the point -3, 8. So we need, for a tangent line, you either need 2 points or you need a slope and a point. We have a point already, we just need the slope. For the slope, that comes from the derivative. So y prime is f prime of x plus g prime of x by the rules of our functions. The derivative of a product, the derivative of a sum is the sum of the derivatives. That's the only, that's the nice one. Product rule and quotient rule, not nice. But everyone remember what it, so let's recite it as a class. What is, just as an aside, you don't have to write this down. The product rule, f prime g, good job, Avery, plus g prime f, good job, Blaze. I love it. Love that we got it memorized. Excellent. Please, please, please practice this as much as possible, because when we talk about the chain rule, these things are going to be at the forefront. They're going to be happening in the background. It's going to be like dribbling and trying to get to a shot. The chain rule is going to be trying to actually make a basket, is the right terminology for basketball, right? I suck at basketball, so I don't know. But I believe it's making a basket. And so you need to, this is going to be your dribbling. If you don't know how to dribble, you can't get to the basket. You can't get to the free throw line. I believe that's what they say. Once again, I'm really bad with basketball. But anyways, y prime. So they gave us the points. They already gave us the x value, -3. So y prime of -3 would be, by definition, f prime of -3 plus g prime of -3. And so we need to look at the graph and the chart to figure these things out. F prime of 3, let's do that. F prime of -3. About to get concerned there for a second. So let's use orange and pink. We don't have those ones yet. Orange for f prime of -3. We'll look at the graph. Here's -3. The tangent line there is the same as the actual line that's present. And that has a slope of down 2 over 2. So that's going to have a slope of -1. Tan line has slope equal to -1. So that implies that f prime of -3 is equal to -1. Because, yes. Because we're trying to find the derivative of f at -3, and the derivative can represent the slope of the tangent line. So specifically at -3, if we drew a tangent line to f there, we would get that orange line, and that line is actually parallel. It's the same line as the line that's already present, which is a slope of -1. Then for pink, for g prime of -3, let's highlight it with pink. G prime of -3 is -2. That's kind of hard to distinguish between the purple. Everyone can see, right? That that's purple, that's pink. Right? It's totally obvious, right? Kidding. On the video recording, it will be, but this is just problem with our medium. But anyway, so it's -2. So this is what did I say? -1 plus -2, which is -3. That's our MTAN. That's our slope. And we already have our point, -3, 8. So y minus y sub 1, so y minus 8 is equal to m, which is -3 times x minus -3, so x plus 3, or y equals -3x minus 9 plus 8, so -1, if you really want to go that route. We're just going to forget that exists. So this is the better way. It's the better way because it tells you exactly where the tangent line is occurring. It tells you that it's occurring at the point. This just tells you so much more. It tells you where the tangent line is occurring at -3, 8, and it tells you what the slope of that tangent line is right off the bat there. That's why I like this format more. Anyways, I'll make it a little bit bigger because it is useful. Because remember, if you're going to use your tangent line for something, if you're going to use your derivative for something, then simplify it. But if you're just being asked to find it, don't bother simplifying. All right. Then we get the trig derivatives. Now, the derivative of sine and cosine, we're just going to give, I'm going to give them to you. So the derivative of sine is positive cosine. Of course, trig would have something nice happening. Trig always has nice stuff. Trig is probably one of the nicest forms of mathematics, save for complex analysis. Complex numbers have some really cool stuff. But trig is always really, really symmetric, so you'd hope the derivatives would be symmetric. The proof of it actually relies, it hinges on the, do you remember what this derivative was? Or this limit? What was this limit equal to? 1. Might help you on an exam problem if you haven't checked already, if you didn't already get it. It might help you that section. But either way, the proof that the derivative of sine is cosine has to rely on that plus, does anyone remember your double angle formulas and your sum formulas? Sine of alpha plus or minus beta, you guys remember that? Good, we all remember it. Excellent, excellent, excellent. That one, not super important for you to memorize. You can always look in a book for that one, but there is a formula for it. And if you use that formula, you should be able to get the right answer.
That one, sine A cosine B plus sine B cosine A.
Yep. I believe that's correct. Been a while since I've taught trig, so I can't remember off the top of my head, but I'm fairly certain because sine of 2 alpha is 2 sine theta cosine theta, or two sine of 2 alpha is 2 sine theta alpha cosine alpha. So yes, I'm fairly confident.
Yeah.
So anyways, but that's besides the point. Just point being is there is a valid mathematical reason why the derivative of sine is equal to cosine. You can also prove it graphically. You can prove it in a lot of different ways, but either way, the derivative of sine is cosine, and the derivative of cosine is sadly not sine, but it is negative sine of x. We can't have it be perfect. Can't have it be perfect. The derivative of sine is cosine, derivative of cosine is negative sine. And so the reason why I've held off on like I could have told you the derivative of sines and cosines in unit 2.2. I could have done that then. I could have done that in but I waited here because in order to find the derivatives of tangent and all the other trig definitions, you have to be able to do the quotient rule. Because if you're looking at it, to try and find the derivative of tangent would be pretty hard to do just by looking at a graph. And there's not really many nice formulas for like nice limits for tangent. But if we remember from trig that this is the same thing as the derivative, so this is equal to ddx of sine of x divided by cosine of x. And then it's a quotient rule. That's your baby f. That's your baby g. Let's use pink instead. Or let's use green. No, red. That's your baby g. So baby f prime is cosine of x. Baby g prime, the derivative of cosine, is negative sine of x. So f prime g minus g prime f all over g squared. You might hear people say low d high minus high d low over low low. That's another way people memorize it. I don't really like it, but it might work for you. Whatever works is fine. So f prime g, so cosine of x times cosine of x minus g prime, which is negative sine of x, times sine of x, all divided by g squared, so cosine squared of x. And that is, well, that doesn't look like a fun derivative. That's going to be cosine squared of x plus sine squared of x, all divided by cosine squared of x. That seems like a really, really bad derivative. Unless, you guys remember one of my favorite sections to teach in Math 127, trig? Remember product identities? Reducing things down. What is cosine squared plus sine squared? 1. So this is 1 over cosine squared, but that's not good enough. We can simplify it more because 1 over cosine is secant. Yes, so this is secant squared of x. So that is to say ddx, just so you have it in your notes very, very clearly, tangent of x is secant squared of x. I should have put that at the very beginning, and this should have been the proof, but either way, the derivative of tangent is secant squared. Then derivative of cotangent by a very, very similar argument, and you can prove this on your own time. Great bonding experience. Do it with your dog, cat, whatever, doesn't matter, but do it with somebody. The derivative of cotangent is negative cosecant squared of x. Very, very similar, but slightly different. Then I gave you a bunch of room for this one. This one's kind of annoying to do, but the derivative of secant is secant of x, tangent of x. Not secant, like we abuse verbiage and say secant tangent. The derivative of secant is secant tangent, but that's not 100% correct because I see students write this all the time. Don't write this down. I'm writing it in pink for that reason. They write this, which is not the same thing. That is saying secant of tangent of x. So it is secant x times tangent x. That is a very, very important distinction, which will play a very, very important role when we talk about chain rule, but we'll get to that soon. Then the derivative of cosecant is very similar. It is negative cosecant cotangent of x. So very, 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 like all the trig formulas are very similar to each other. So if you want a trick to memorize, so you don't have to memorize 6 formulas, you should memorize derivative sine, derivative cosine, derivative tangent. Those ones definitely. And then secant, cosecant, and cotangent can all be figured out by realizing that it's very, very symmetric. That's the way I memorized it, at least. So my brain kind of tries to fill them out each time. Granted, like when I was taking it, now I have it memorized because I just teach it every year or so, and so I just keep saying it over and over again. But either way, so let's look at some examples. So that's x squared times sine of x. We're going to take its derivative. That's a product. And so I want to show you what you need, like what I would like you to get to. So I look at this. I identify my f and my g. My baby f is x squared. My baby g is sine squared. And I do this all at the same time. I do the derivative, I do the product rule at the same time. So this is where I'd like you to get to. If you're not there yet, that's okay. It takes time to do this. I wasn't good at this the first time I did it either. It took me a lot of practice. But this is what I'd like you to get to by the end of the semester. So f prime of x, capital, like the actual function, is f prime. The derivative of f prime would be 2x. So the derivative of f would be 2x. So f prime g, so 2x sine x, plus g prime, the derivative of sine is cosine, so plus cosine of x times g, so x, or times f, x squared. F prime g plus g prime f. If you can do it all in one go, please do so. I will give you full credit either way. But if you want to see the additional work, or if that's how you like to do it, be my guest. But that's where I'd like you to get. My goal would be that you don't need to write down what f and g are and do it. The only exception is if you're dealing with like multiple product rules and multiple chain rules, that can become a little bit challenging to work with. And so it might be a good idea in those cases to do it. But either way, this one, x cubed plus natural log of x over tangent of x. So this is your f, this is your g, and so k prime. And so I'm going to do it again. The way I would do it myself, f prime g minus g prime f all over g squared. So what is f prime? Take a second. 3x squared plus the natural log. That one has the derivative of 1 over x. So f prime times g, so tangent of x, minus g prime, the derivative of tangent. I don't expect you to have that memorized yet. We just learned it. The derivative of tangent is secant squared times f. So that's x cubed plus natural log of x, all divided by g squared. So tangent squared of x. And since we're not going to use our derivative for anything, we will just leave it like that in all its glory. Yes, Jake.
How do we know the log x was 1 over x cubed?
Oh, that was given in 2.2, the derivative of natural log. And also, speaking of which, it's going to be a little bit later here at the very end of this section, at the end of 2.3, I have all the derivative rules that we've learned so far. So you can use this as a little cheat sheet to practice. Like take 2 sheets of paper and kind of like cover up the answer. And it's a good little cheat sheet. Anyways. In the interest of time, since we are behind, there's a lot to go through here. I'm going to skip these ones. Well, I'm going to skip the first one. I'd like you guys to do that on your own. I'll fill it in during the break so you can take a picture of it, so you can see the answer. But this one right here, this one is 2 separate product rules. There is a product rule with the first term because it's e to the w times cosine of w, and then there's a second product rule with the w squared plus 1 times secant of w. So this is our baby f, this is our baby g, and then for our second set, this is our green baby f and our purple baby g. They're not derivatives. They're these are 2 parts of the function. They're 2 separate products, and because they're being multiplied together, but that middle sign is a subtraction, so we're going to treat them as separate. Does that make sense?
Yeah, but when it said we're using the product rule twice, wasn't the product rule of derivative specific thing?
Yeah, we're going to be taking the derivative of that function. So we need to take the derivative of the whole function, and so there's 2 pieces to it. There's one piece that's the first, the EW cosine W, and the second piece, W squared plus 1 times secant W. Is that, I don't know if that's answering your question.
It's probably listed since this is D, above A, does it say take the derivative of the
Yes.
one function? Okay, my bad.
Yes.
Because we've seen it also where it says like PDX of T, you would equal that, right?
Yes, so but that would provide, it would say that that's T prime.
Gotcha.
So, yep. So T prime of W is, I'm going to put it in brackets so we can see that where each piece comes from, but you don't have to. F prime G, derivative of E is itself. E to the W, cosine W. The derivative of cosine, so G prime, is negative sine. So since it's the product rule, it will be F prime G plus G prime. But since this is negative cosine, I'm going to write minus sine. Minus sine of W, E to the W. Like it would be totally fine to write plus negative sine of W, E to the W. That would be fine too, but I just wanted to simplify it, make it look pretty. Save on some parentheses if we don't like, but it's not wrong to write it that way. And then minus in brackets, F prime is 2W secant W plus G prime. The derivative of secant is secant W tangent W. So secant W tangent W times W squared plus 1. That's G prime F. That is our answer.
F prime,
Sure, we'll use an oval this time.
F prime was what?
The
E to the W.
derivative of the exponential function is itself. So F prime is e to the W. G prime is negative sine of W. F prime, baby green F prime is 2W, and baby purple G prime is secant of W, tangent of W.
You said of the exponential function, but is that only when it's E? When E?
Only when it's E, yeah. The natural base. All right. So at the core of them, so we know that the derivative is it can represent the slope of a tangent line when you plug in a value, right? It represents that when you plug in a specific value. But when you're just looking at it willy-nilly like this, it's a function. And so we can take derivatives of functions. So the question then becomes, can we take derivatives of derivatives? Can we take derivatives of derivatives of derivatives? Can we do this process indefinitely? And the answer is yes. Higher order derivatives. So you can take the second derivative, you can take the third derivative, the fourth derivative, all and on forever. And so here's the notation. So if you're taking the second derivative, that's double prime, F double prime or Y double prime. And that's in Newtonian notation or prime notation. And then in Leibniz's notation, that's d squared y over dx squared or d squared f over dx squared. The third derivative, d cubed y over dx cubed or d cubed f over dx cubed. Now the question might be, why? Why is that the case? And the reason for this is that if you take the derivative of the derivative, you see that you only get two d's. You don't get an extra y, but you do get two dx's. So that's why the notation is d squared y over dx squared. That's the reason for the notation, but anywho. And then if you're taking the nth derivative, so after the third derivative, it starts to become really annoying to write tick marks. And so it might just be easier to write parentheses 3, parentheses 4, parentheses 5, and so on and so forth. And then if you're talking about the nth derivative, that would be, you just write an n, a generic n. So for the function f of x equals x cubed minus 11x squared plus 3x plus 2, find the fourth derivative. So let's in order to find the fourth derivative, you need to know the third derivative. In order to know the third derivative, you need to know the second. In order to know the second, you need to know the first. So we need to find the first derivative, f prime, 3x squared minus 22x plus 3. The second derivative, so I should write of x, f double prime of x is 6x minus 22. The third derivative is going to be 6. And so the fourth derivative, and you can use 4 tick marks if you really want to, but the fourth derivative is 0. So then the question that I pose to you, an observation, if f is a polynomial of degree n, so if it was degree 5, it would have an x to the 5th power or whatever. What is the n plus 1th derivative? Each time you take a derivative, you reduce the power by 1 when it's talking about a polynomial. So if you take it n plus 1 times, you're going to reduce the power by n plus 1 times. It will go all the way, it will go all the way down to 0. Or a degree n polynomial. I only bring this up because there's they love to do this on the GRE, the math GRE, and then also the Putnam exam. By the way, as an aside, just a fun little tidbit. There's a thing called the Putnam exam. Has anybody heard of it? It's a math exam. The average score on it is a 0. It's out of, I think, 4 points. If you get a half of a point, that's considered a really good score. And like usually that's enough to get you into grad school. So if you get a half a point, it's a very, very hard exam. Very few people get more than about half a point. And they love questions like this, though the Putnam exam is much harder than that. But like saying if f of x is equal to x to the 100 and the 1002 plus blah 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 blah, find f prime, sorry, f to the 1003 of x. They don't actually expect you to find 1003 derivatives. They don't want you to do that. They just want you to observe what's happening. So that's a tricky little problem that they do. Anywho, I'm getting sidetracked. Not a good idea right now. That's your guys' fault, not mine. So find y triple prime. Find y triple prime. If y is equal to x cubed natural log of x. So in order to find the third prime, we need to find the second. In order to find the second, we need to find the first. So let's find the first derivative. F prime, y prime. So this is your f, this is your g. So y prime will equal 3x squared natural log of x plus g prime f, so 1 over x times x cubed. This is a product rule, yes, good. Now, what was my golden rule about simplification? If you're going to use something, simplify it. Since we're going to use this, to find y double prime, let's simplify first.
Second term, because they have x's, not
Mhm.
the actual patient.
Yeah, exactly right. So the second term, the 1 over x times x cubed. We can't really do anything with the 3x squared natural log of x. I mean, you can use some logarithm properties to bring it up, but that would cause more problems than solutions. But that 1 over x times x cubed, if you leave it as is, you're going to have to do a product rule with a 1 over x function, which you can finagle, but it's just going to make it way more muddy. And remember, we're trying to find the third derivative, so we get an even muddier thing, and then it will be even more messy. But because 1 over x and x cubed can cancel just a little bit, that'll make things a little bit easier. So this is 3x squared natural log of x plus x squared. Whenever you need to use something, simplify it so that you can work with the smallest bits. So then we got to find y double prime. Y double prime will equal, this will be my baby f, this will be my baby g. So f prime is 6x times g natural log of x plus g prime, which is 1 over x times f, which is 3x squared. And then don't forget about your plus 2x, the derivative of x squared, which is 2x. Sometimes that happens. Remember, we got to take the derivative of the whole thing. And so once again, we're going to simplify this because we're dealing with a we're dealing with a situation where we're trying to find the third derivative, and we're going to simplify it so that we're going to be able to use the easiest version of the function. So this right here will cancel, and so we'll have a 3x plus a 2x. So this really simplifies to 6x natural log of x plus 5x. And so that would mean that y triple prime, our final answer, will be f prime. So 6 natural log of x. This is our f, this is our g. So f prime would be 6 times g, which is natural log of x, plus g prime, which is 1 over x times f, which is 6x. And then don't forget about the derivative of 5x, which would be 5. And so We could simplify it, but since I'm not asking you to I'm not asking you to do anything with the third derivative, you could box it in here, or you could simplify it nicely to write it as 6 natural log of x plus 11. Either way is fine with me since I'm only asking for the third derivative. I'm not asking you to do anything with it. All right, any questions on that? I'm gonna look at our schedule real quick just to make sure. We're supposed to go over the chain rule today, so we can start that soon. So this one here is a really cool one. So g of t is equal to 5 e to the t sine t. E functions and product rules are always fun because they just stick around. So go ahead and do the first derivative. I'm going to slowly fill in details. And I'll write more detail than normal. So they don't expect you to have the sine and cosine derivatives memorized already. Those it takes time. Much like this function because it's measured in t. It takes time.
I was gonna ask you about that, so doesn't matter the coefficient, on the E exponential function, it's always still the same, including the same coefficient?
Well, so that's by two different rules. So there's the constant multiple rule that says that if you have a constant, you can just pull it out front for a derivative and it just sticks around. And then the derivative of e to the t is itself. So that 5 sticking around is based on the constant multiple rule. That'll happen for any function, not just e. So g prime of t.
Well, we usually wouldn't you usually want to apply the power rule instead of the constant rule? I guess we can choose.
The power rule only works if it's x raised to a number.
Oh,
Or-
there's no coefficient?
Well, the coefficient doesn't really.
Oh, I get what you mean. The exponent itself is, okay, I got you.
Mhm.
The exponent can't be a variable.
Yes, exactly right. 5 e to the t. All right. So you should get this. You should get 5 e to the t sine t plus cosine t 5 e to the t. Or preferably 5 e to the t cosine t for that second term, just because we usually like to see our exponential function first, then trig, then polynomials. Or sorry, exponentials, then polynomials, then trig, then inverse trig, typically speaking, but that's just convention. So we want to find the second derivative, right? Now the question then becomes, do we do it right now? Because there's nothing that can quote unquote simplify. So if we do it like this, if we take a derivative like this, we have to do 2 product rules. It's not wrong, it's not bad, it's just 2 extra pieces of work. However, I would notice that there's a common factor of 5 e to the t. So this is 5 e to the t times sine of t plus cosine of t. And the reason why I noticed that and the reason why I care about that is that makes it so I only have to do 1 product rule instead of 2. Is it better? Is it worse? You save yourself maybe 5 seconds on an exam. So it's not that big of a deal, but just to show us that we can practice our algebra skills, have some fun factoring. Now, who doesn't love a good factoring problem? Me, Phil. Who said that? No. All right, so this is my little baby f. This is my baby g. So f prime is 5 e to the t times g, which is sine of t plus cosine of t, plus g prime. G prime is going to be, derivative of sine is cosine, plus derivative of cosine, which would be negative sine, so cosine of t minus sine of t, times f, which is 5 e to the t. And since we're not asked to simplify, we can leave it as is, but if you distribute in that 5 e to the t, you'll notice that you get, or 10 e to the t cosine t. Pretty nifty. And so the reason why I wanted to simplify this for the challenge for fun problem for home time is find the 12th derivative. Do I actually want you to find 12 derivatives? No, I don't. I want you to look for a pattern. Because one of the cool things about trig and exponentials is that they always have patterns. They love to have patterns. So please feel free to try that one at home. I got the answer for you there. Very, very cool stuff. Yes.
I see the expanded one, why that one works, but how does that end up being 10E if you wanted to simplify it?
Sure. So if you simplify it, you distribute in the 5t e to the t's. The sine t here and this sine t end up canceling out, and you just have 5e to the cosine t plus 5e to the t cosine t, which ends up being 10e to the t cosine t.
It's not a negative 5ET at the end.
That's a times. That's
Okay.
clearly a times, guys. No, that looks bad. Let's just make that. Let's just do this better. Let's do whoop, like that. Call it good. Fair point. Fair point. All right. Physics application, unless there's any questions on that. I'm sorry to rush along a little bit. I don't like to do so. But this one, physics application. So we know the position function is labeled S of t. The velocity function is v of t. And acceleration is the next derivative. Feet per second is what they usually say. Feet per second squared or feet per second per second. And I hope you guys remember the reason why it comes from the definition of the derivative is that v of t, like, so if you're doing the derivative of velocity, which is the acceleration, you'd be doing v of t minus v of h, or sorry, v of t minus v of a over t minus a, where v of t is measured in feet per second and t minus a is measured in seconds to get feet per second per second. But either way, that's not super useful here. That's a physics thing, and we're going to barely touch physics, in my opinion. Acceleration is a of t. And so v of t is equal to s prime of t. A of t is v prime of t, which is s double prime of t. So it's the second derivative of the position. Acceleration is how fast you get up to where to your speed. This goes even further in physics. They start talking about the third derivative and what that means. And the fourth derivative, I believe there's torque and then there's jerk. I think are the two things, but I'm not a physicist, so I don't know. So don't quote me on that. Talk to your physics professors for that situation. But I believe, if memory serves, there's information that can be gathered in a physical sense from third and fourth derivatives. But either way, position of a particle is given by, I don't know how they measured it, but let's just say that the position is 1/4 t to the fourth plus t cubed, 3t cubed plus 7, where t is measured in seconds and s is measured in feet, because this is America. We use American measurements. Find the velocity and acceleration functions. So so v of t would be the derivative of s. That's going to be negative t cubed plus 9t squared plus 0. And then a of t is the derivative of that. Negative 3t squared plus 18t. Now, this second problem is really just another kind of reminder and warm up for unit 3, which is going to do a lot with nonlinear inequalities. So find the intervals on which the particle is accelerating, which would mean when a of t is positive. So a of t being positive, that means negative 3t squared plus 18t needs to be greater than 0. You guys remember how to solve a nonlinear inequality? Yes, we do. Excellent, excellent, excellent. You get one side equal to 0, already done for us. And then the other side, you factor as much as possible. I'm going to factor out a negative 3t and get t minus 6. Has to be greater than 0. So your VIPs, your very important points, the not points, I know they're values, but Viv doesn't have the nice ring to it. So t equals 0 and 6. And I'm going to start my number line at 0 because we can't talk about negative time. Right? We can't talk about negative time. You can even write that. Can't have negative time. And so then here's 6. And so we just plug in a test value, right? Plug in, like, let's say x equals 1 or t equals 1 and t equals 7. And then the way I do it, though, if you like it a certain way, that's your prerogative. It's your own Bob Ross, do it yourself. Plugging in 1 into it, the way I look at it is I'm just looking at the signs. The first term, since it's negative 3t, will be negative, and then plugging in negative 1 into t minus 6, you also get a negatives. So it's positive here, which is a piece that I want. And then if you plug in 7, you're going to get negative times a positive, which is a negative. That's the piece I don't want. So it's accelerating on 0 to 6. For the first 6 seconds, it's accelerating, and then it starts decelerating. Yes.
So it's only based off the application that we're looking for the positive.
That's correct. Since we're saying that it's accelerating, if I asked for when it's decelerating, we would say from 6 to positive infinity.
Because if we were just, saying where if we were just solving the inequality, like without any work problem context, right, it would just be less than 6.
Yes. Well, no, actually, it would still be from 0 to 6. It's going to be like, if you continue the number line to the left, if you plug in like -1, you'll see that you get a positive times a, wait. You'll get a negative, positive. What am I doing wrong? And then
You would divide away the -3, which you put the sign on both, so then you'd have t is less than 0 and t is less than 6.
We can just operate.
positive times a, oh yeah, no, you get a positive times a negative and it would be negative there. So if you continuous on, you get negative over here too. But we don't need to.
Guys, you don't have any question, just because you brought it up here,
Yeah.
on the previous one, does that mean then that the third derivative of the position will always give you acceleration?
The second derivative will always give you acceleration. The first derivative is always velocity. The second derivative is always acceleration. And then physics might go further, but we're in this course, we're only going to scratch the surface of physics. And then just omit this one. It's not useful. We're going to skip it. So once again, here are the derivative rules. All of them. These ones you kind of get to the point where they're your bread and butter, and you won't you kind of have to know them. Like you memorize them just by practicing it so much. These are the ones that require more practice. To be clear though, this one here. Come on, give me a box, please. That one, and let me copy it. And this one do not need to be memorized. All the other ones are fair game. All the other ones are fair game and need to be memorized and be able to be used. And I don't like doing that very often. I don't like requiring you guys to memorize things. But this is one of those things that calculus, you're going to have 3 semesters of it. If you plan on taking, if you plan on going into a STEM degree, you're probably going to have to take math 182 and 283. And you're going to be taking derivatives all the time in those classes. So you need to know these. You just have to. It will make your life so much simpler if you don't have to keep referring back to it. So I'm going to require that now so that you can be prepared for 182 and beyond. The trick though, one trick to remember is that which ones have the negative signs for the trig functions? All the co-functions have a minus sign. Derivative of cosine is negative sine. Derivative of cotangent is negative cosecant squared. Derivative of cosecant is negative cosecant x cotangent x. So that's a nice nifty way to remember which ones have the negative sign. And that might be a way to kind of memorize it. If you remember derivative of sine, cosine, and tangent, and secant, you can get cotangent and cosecant by just, or if you memorize sine, tangent, and secant, you can get cosine, cotangent, and cosecant kind of by just deduction. But either way. All right. Any questions on that before we move on to chain rule? The most important rule that you will be using all over the time, all the time. Just as a small note, this problem right here. You know, the person who said I can do whatever I want. That's the person who said it. That's Dr. Devenatz. He was my calc professor, and then he was also my real analysis professor. And this is one of the exam questions he had. It was pretty gnarly. Thank you, Dr. Devenetz, for that awful problem. Anywho, so the chain rule, the most important rule. Let f and g be differentiable functions. Otherwise, this doesn't make any sense. Then if you define f, capital F, to be the composition, f composed of g, f of g, which is defined as f of x equals f of g of x, then f is also differentiable, and it is calculated as such. F prime, capital F prime that is d dx of f of g of x, which is f prime of g of x times g prime of x. They say the derivative of the outside times the derivative of the inside. Now I put that in quotation marks because that's not 100% true in its statement. Derivative of the outside times the derivative of the inside. It's not that. It's the derivative of the outside function evaluated the inside times the derivative of the inside. Because it's not f prime of x, it's f prime of g of x. That's the formula. Now, going back to Leibniz's notation for a second. If you have a composition of functions, what you're saying is that y is equal to an f of u, where u is a function of x. And so this is why the rest of Europe was able to advance so much faster, because they thought it, they looked at it like a fraction, and you could see that the derivative of y with respect to x instead of with respect to u is dy du times du dx. And you'd see the du's cancel, quote unquote. Don't write that down, but that's what they noticed. They were like, well, I could do derivative of y with respect to u, du, and then du dx. It should work out. And so that was one way they learned about the chain rule faster than England did, because of those types of things. I think that the Leibniz notation is good for proofs, but Newton's notation is better for practice, for procedural problems. So I'm going to show you both methods and let you decide. And then I'll slowly start to show you maybe a better way to do it as well. So this is the first way you're introduced to it. And then I'll introduce my own way that I've developed that I feel like makes it better. But just so we have a bunch of different ways to see things. So if h of x is equal to sine of x squared, find h prime of x, because it's not just going to be cosine of x squared. The derivative of sine of x was cosine of x, but the derivative of sine of x squared is something completely different. And yeah, you could do that whole, you could do some trig function stuff to do some things, but let's assume we don't remember our trig, so let's do that. So here, you'd have y is equal to sine of u, and u is equal to x squared. So then by the Leibniz notation, the derivative of h prime would be dy dx, which would be dy u times du dx. The derivative of sine of u with respect to u would be cosine of u. And the derivative of u with respect to x, the derivative of u equals x squared would be 2x. But we want, what's u? U is x squared. So this is really 2x cosine of x squared. I do find Leibniz notation to be a little bit more convoluted. So if that's not jiving with your personality, that's fine. Don't worry about it. Like every single way is valid. So I'm going to show you this way, and then on the next one, I'll show you my method, which is the way that I think is the best to understand it, but I'm biased. So if you prefer one way over the other, please continue to do so. The outside function is the sine function. So the outside function f of x will equal sine of x, and the inside function g of x will equal x squared. Then f prime of x would be cosine of x. Which would tell us that f, like, so remember the formula is f prime of g of x. So this would mean that f prime of g of x, I'm going quick. I'm going too fast on this situation. I'm going to slow down for a second. I realize that. The outside function is sine of x, and the inside of the function is x squared. So f prime would be cosine of x, so then f prime of g of x would be f prime of x squared, which is going to be cosine of x squared. Remember, when you like, just like with x plus h, you're going to replace every instance of x in the function with an x squared here. That's why f prime of g of x is cosine of x squared. G prime of x is 2x. So h prime of x will be f prime of x, or f prime of g of x times g prime of x, which is cosine of x squared times 2x, or preferably 2x cosine of x squared. If you're lost, that's okay. It's okay. This is the first time we're doing this. Not easy. Math has never been easy. These are tricky problems. So let's do it again using Leibniz notation and composition method, and then I will show you my method as well, so you can get a taste of all of them and see which one you want to do. In this case, you got k of x is equal to x squared plus x minus 1 to the third power. Yeah, we could FOIL it out, and then we get just a big polynomial. We could do it that way. That would be fine. But but what if that was the 30th power? Do you really want to FOIL out 30 times? I don't want to. So keep in mind, this is more generalized than just to the third power. So in Leibniz's notation, the outside function is that third power. So y would equal u cubed, and u would equal x squared plus x minus 1. So dy du would be 3u squared, and du dx would equal 2x plus 1. Maybe when you see it like that, instead of like the way I did it above, it might make it a little bit better. So if this works better for you, awesome. If not, no deal. So then dk dx is going to be dy du times du dx. So that's going to be 3u squared times 2x plus 1. Or once we change it to all in terms of x, 3 times x squared plus x minus 1 to the second power times 2x plus 1. The other thing I will say, and I'm sounding like a broken record and I don't care, this gets much easier the more you practice it. And I know that's true of basically anything in life, right? But with the chain rule, the quotient rule, and the product rule, they become so, like, it's exponentially easier the more you practice it. It's not like one of those things where it's linear, or kind of like quadratic or anything like that, and how you improve, or that dreaded game at Chuck E. Cheese where you have to make it into the jug. You have to throw a ball and get it into the jug. I've gotten 3 in a row so far. 5 in a row gives you 250 tickets. I'm trying to get that. I'm trying to get that big prize right now. I want to get to the point where I can do 5 in a row. But regardless, that's not an exponential growth. That takes a lot of practice. This, however, the more you practice it, the better you get at a substantial rate. So please, tonight, practice. Please. Just look at like 3 problems, do 3 practice problems, then come back tomorrow, do 3 more practice problems, then touch it maybe the end of the week. But please do it, please. Especially since you have a quiz on it on Wednesday. You will thank yourself Future you will thank you for doing a practice tonight. Anyways, the composition method, the outside function is that x cubed. The inside function is that x squared plus x minus 1. Do you guys remember doing this in 126? Like find two functions that compose this. You guys remember that? You talked about composition, but hopefully you talked about decomposition as well. And that's why we had you studying that, why you had you practicing it. Anywho, so f prime would be 3x squared, which means that f prime of g of x would be 3 times x squared plus x minus 1 to the second power. Because you're plugging in g in for x. G is x squared plus x minus 1, so plugging that in for x, you get 3 times x squared plus x minus 1. G prime is 2x plus 1. So at the end of the day, k prime of x, or dk dx, whatever you want to call it, is 3 times x squared plus x minus 1 squared times 2x plus 1. And that is the answer. If you don't like those methods, that's okay. I hope my third method will be better. My third method takes into consideration the fact that it's the derivative of the outside times the derivative of the inside. So let's do one of them, and then we will we'll take a break. We'll do this one, and then we'll move on. We'll take a break, and then we'll come back. So first and foremost, I see that as a radical, and there's no rule that tells you the derivatives of radicals in its current state of things. You need to convert it to exponential form. This is 2 minus 9x to the 1/4 power. The way I like to do it, and this becomes especially, the way I do it becomes especially easier once you have practiced the product rule and the quotient rule and all of your main rules, the power rule, the constant rule, your sines, cosines, and all that. It becomes a lot easier too if you do that. So derivative of the outside function is that 1/4 power. So the derivative of that, p prime of x, actually I'm going to write that a little bit higher up. P prime of x would be 1/4 times something to the negative 3/4, right? That would be the power rule in action for the outside function, that 1/4 power. But it's the derivative of the outside evaluated at the inside. So I'm going to keep the 2 minus 9x in here. Any questions so far? So once again, that's the derivative of the outside function evaluated at the inside. And what I mean by evaluate is kind of an abusive terminology, because it's not really evaluating a function. You're not plugging in a specific number, but it's derivative of the outside when you plug in the inside function. That's why it's still 2 minus 9x, then times ddx of 2 minus 9x. So that you don't have to do it all in separate steps and bring them all together. You're doing it all at once. And then we just need to write one more step, because now we need to take the derivative of that secondary piece. So p prime of x is therefore 1/4 times 2 minus 9x to the negative 3/4 times negative 9. The derivative of 2 minus 9x would be negative 9. Or if you want to make it look pretty, or negative 9/4 times 2 minus 9x to the negative 3/4. However you want to write it, though, is chill with me. Is totes chill, as the kids say, right? You still say totes chill? Blaze, do you say totes chill? No. Alex, do you say totes chill? Is that just is that an older person thing now? Okay. Wait, is this got Riz? That's what you mean. That's the thing, right? Riz. You guys have some silly lingo. I like it. Way cooler than millennial lingo and before, especially Gen X lingo. Burn on Gen X. But anyways, that's the way I like to do it. Maybe we should do one more and then take a break so you can see this again in action. This one right here. Oh, well, this one has a product rule. So let's do, yeah. we'll come back. We'll skip ahead to this one to really hone in. Let's take a break. Let's take a break. Let's come back together at 12:05. All right. People watching the recording, do some guided meditation, whatever you want to do. And we're back. Ready to start more chain rule. So we can actually still do it on this one. So this is now a product rule because there's a product of two functions. There's z to the fifth and there's 1 minus 3z to the 2/3. So that's right. You can have a chain rule within a product rule. You can have a product rule within a chain rule. You can have two product rules with both chain rules. There are so many combinations. It is limitless, the amount of things that you can do with chain rule. This is what opens up all the functions. Up until this point, we've been really restricted, but now we can do the derivative of any function. Once we learn the chain rule, we can do the derivative of any function. So we still need to do this whole thing. This is f, this is g. So f prime is 5z to the fourth. Nothing too terrible. So this is my notation for finding. So g is going to require a chain rule because it's a function within a function. G prime. The outer function is that 2/3 power. And so the 2/3 power derivative by the power rule would be 2/3 to the negative 1/3. Because it'll be 2/3 minus 1, which would be negative 1/3. And it's the derivative of the outside function evaluated at the inside function. So the inside should be 1 minus 3z, then times the derivative, so d dz. Though if you prefer, you can do parentheses and then a prime symbol if you want, or an apostrophe. Both are fine. D dz of 1 minus 3z. But the derivative of 1 minus 3z is negative 3, thereby canceling out that negative, but you got to keep that, or canceling out the 3, but you got to keep the negative. The derivative. So what I meant to, like what I said but didn't write out, is instead of writing d dz of 1 minus 3z, you could write 1 minus 3z prime. The only reason why I don't like doing that personally, there's two reasons. First reason is that sometimes that prime can look like a smudge mark when you're on an exam, and maybe you forget about it and you just say, oh, maybe that was just a smudge and I'll erase it. And so I don't actually find the derivative. That can happen. So that's why I don't do it. The other reason is that when we talk about related rates in a little bit, I like to use the notation to say what I'm taking the derivative of with respect to. So I like to use the DDC. But if you want to use the prime notation, that's all you, that's your fine. That's your prerogative. That's okay too. So G prime then is negative 2 times 1 minus 3z to the negative 1/3. Yes.
So here, why would you not write df to dz if you're doing ddz? I like ddz way better, but it's still confusing to me.
So why didn't I write df or dgdz?
For the 1 minus 3z, why'd you write d over dz and not df over dz?
Excellent question. So I'm glad you brought it up because this is a thing that we need to keep reminding ourselves. df dz or dg dz or dy dz or dy dx, whatever. That is a derivative. ddz or ddx or ddy or whatever it is, that is the process of taking a derivative. So when you see d without a number on, like without a letter on top, that means you're taking the derivative of whatever inside the parentheses. That is the notation. dy dx is a derivative. ddx is taking a derivative. Does that make sense?
Yeah.
Clear?
Process for thing.
Yes.
Two letters on top and bottom, that's a thing.
Yes, that's a thing, whereas this is an operation. So that's any other questions on how I got the derivative of G prime, or the derivative of G? We're gonna get plenty of practice with this, so that's the good news. So now we just need to fill it in the blank. Fill in the blank of the derivative rules. The product rule is f prime G plus G prime F. F prime G plus G prime F. So f prime, capital F prime, that is f prime G, so 5z to the 4th times 1 minus 3z to the 2/3 plus G prime, which would be minus now because G prime is negative 2z. So you can keep it as plus negative, but I prefer if you just write it as negative 2 times 1 minus 3z to the negative 1/3
times z to the 5th. And that is our answer. Any questions? If you look beyond, there's a lot of derivative problems. I put a lot of them on there because this is something that really just needs practice. And like, depending on timing, I might spend some time, I might skip a few problems and record a video for you guys to watch to do the other problems. But anyways, this one, y is equal to sine to the 4th of x over x cubed minus 8. One of the big things that you need to remember. When you have this notation, this means sine of x all raised to the 4th power. So it's a chain rule. Because the outer function is that 4th power, the inner function is sine. It happens way too often where students see this and they just want to write it as 4 sine cubed of x by the power rule. But that's not enough. This requires a chain rule. So this is my f. This is my g. F prime. The derivative of sine of x to the 4th power. The outer function is that 4th power. Outer function is here. The derivative of 4th power would be 4 times it to the 3rd. Times the derivative, so d dx of sine of x. Derivative of the outside times the derivative of the inside. This is my method. I hope you like it more. If you like the other way of doing like the composition rule or the Leibniz notation, that's okay too. This derivative of sine is cosine, leading us to f prime being 4 sine cubed of x cosine of x. That derivative is cosine. Derivative of sine is cosine. So f prime g minus g prime f all over g squared. F prime g minus g prime f all over g squared. Has anybody woken up saying in a cold sweat yet? I should see a lot of hands. I'm not seeing a lot of hands. It's okay. It's all right. We'll get there. G prime is 3x squared. G prime was nice and quick. So y prime or dy dx, however you want to write it, is f prime. So 4 sine cubed of x cosine of x times g, which is 3x squared, minus g prime, which is 3x squared, times f, which is sine the 4th of x, all divided by x cubed minus 8 to the 2nd power. $40. I'm just gonna check something really quick on timing, and I'll come right back to that. That one, that one, that one, that one, that one, that one, that one. We can skip those. Okay, cool. And then there's that, and that's it. Cool. All right, I think we'll be fine. I think we're on time. We're on top target. Any questions on this one? Yes.
Sure. How,
No such thing.
so I get, since we're using the quotient rule, like, why don't we do it again? Like, why don't we then use our numerator as f and then the bottom as another g? Would we get the same thing?
Well, if we did that, then we'd be taking the second derivative.
Oh, okay, cool. That's helpful.
Yes.
Okay, that is what that is.
And by the way, yes, please.
First term times x minus 8 squared.
Yep. You're right. Thank you. X cubed minus 8. Thank you for catching that. teaching calculus, one of the hard things is saying f prime g minus g prime f and saying what f and g are at the same time. So thank you for catching that. Okay. One other thing, by the way, just as a nifty little trick. So if you don't want to memorize the quotient rule, you can actually, now that we know the chain rule, you can just memorize the product rule and call it good. Because anytime you have this over this, you can write it as a product that. So effectively, you don't like, if you want to, you can only like, you can just memorize the product rule and convert any quotient into a product. Just as a nifty little trick. And you'll get full credit. The only reason why I sometimes avoid that is if I'm going to be using the derivative. If I'm going to be using the derivative, then that's going to be a little bit more convoluted. So, but if you're just being asked to find the derivative, you can do it that way if you're really in a pinch. This one, sine of square root of t plus the square root of sine of t. So this is two different chain rules. One of them is that the outer function is sine and the inner function is the square root, whereas the second piece, the outer function is the square root and the inner function is sine. So first and foremost, I'm just going to rewrite this as sine of t to the 1/2 plus the quantity sine of t all raised to the 1/2. So the derivative of this is going to be so f prime of t, the outer function for the first term. The outer function is sine. And the derivative of sine is cosine. So this will be cosine of t to the 1/2 times the derivative. So d dt of t to the 1/2. Now I'd like you to do the second piece, like set up the second piece to finish it. I will still fill in details. The outer function in the second term's case is that 1/2 power. So it should be (1/2) sine of t to the negative 1/2, because it's going to be 1/2 minus 1. That gives you the negative 1/2, that power rule. Then times the derivative of the inside, so d dt of sine of t. And as you get better and better and better at this, you don't have to write the DDT. You can just do it all in one step if you feel comfortable. If you feel comfortable doing it all in one step, be my guest. That is encouraged. You get to a point if you practice this enough that you can do it in your head. And I'd like you to get to that point. It makes it much nicer, much quicker. So at the end of the day, that's going to be cosine of t to the 1/2 times 1/2 t to the negative 1/2 plus 1/2 sine of t to the negative 1/2 times cosine of t. Any questions on that? It's really okay if there are some. This is probably the hardest rule when you first encounter it. It becomes much, just like with everything, I've said it a billion times at this point, but it becomes much easier the more times you practice it. So please, 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 please practice it a little bit tonight. Like, you know, maybe a hot date tonight, say, hold on, sweetie, I need to do this. The middle of your date, just do this. Guarantee it. They'll respect you so much more. Say, man, that person put their education first. I am second to their education, and that's an important quality in a person. Kidding. They should choose you first, but whatever. Okay, next one. H of W, yeah, H of W is equal to sine of cosine of W squared plus 1. This is a double chain rule. It's a double chain rule. It's a chain rule within a chain rule. So, but we're still going to approach it the same way. The derivative of the outside function, the most outer function is sine. And then the inner function in relation to sine is cosine of W squared plus 1. So H prime of W, and this is why I like my notation, is going to be cosine because the derivative of sine is cosine. So it's cosine of w squared plus 1 times the derivative. So dw of the inside, cosine of w squared plus 1. By the way, why the chain rule works is a great question, and there is a proof of it, of course. And if you want to see it, please feel free to ask, but we're already behind as it is, so I'm not going to do it during class time. But there's also, as I said before, there's a mathematician named 3 Blue 1 Brown who has really, really good videos like for visual aspects of calculus. And so he does explain the chain rule there that might resonate with you and make it make more sense to you. But either way, so then this. So I'm going to rewrite, this is cosine of w squared plus 1 times, this time, the derivative ddw of cosine of w squared plus 1. The derivative of cosine, that's the hour function, is negative sine. So it's times negative sine of the inside, w squared plus 1, times ddw of w squared plus 1. That's why I like my method more, personally, because it allows you to do multiple chain rules and just kind of string it along until you finally finish. Though, once you get good at this, you can just skip doing it in steps and just do it all at once. So at the end of the day, that would be negative 2w cosine of w squared plus 1 times sine of w squared plus 1. And how you jumble it up is your prerogative. It's your choice. Just the convention is to put constants, exponentials, polynomials, trig, and then trig, logarithms, and inverse trig kind of all get jumbled however you want. It just looks the nicest that way. Any questions? All right. The next one, k of x is equal to e to the x cubed minus 7x squared plus 2. Now, I told you the derivative of e is itself. And that's only half true. The derivative of e to the x is itself. This is a chain rule because this is e, not the derivative of e to the x. This is the derivative of e to the x cubed minus 7x squared plus 2. So the outer function here is e, and the inner function is x cubed minus 7x squared plus 2. So this would be k prime of x. The outside function is e. The derivative of e is itself. So it's the derivative of the outside, e, evaluated the inside. So it's e to the x cubed minus 7x squared plus 2 times the derivative of the inside. X cubed minus 7x squared plus 2. And so at the end of the day, k prime of x would therefore be e to the x cubed minus 7x squared plus 2 times 3x squared minus 14x. And that's your derivative.
Okay. Next ones, we're gonna skip. No. I changed these ones around. That's right. I finally fixed it in my notes. Okay. The derivative of y, t of y, where it's equal to pi to the cotangent of y. So, as a reminder, the derivative of a to the x is natural log of a times a to the x. So the outer function is the exponential. It's pi to the x, and the inner function is cotangent of y. So t prime is the outside function's derivative, so that'd be natural log of pi
times pi to the x, but it's evaluated the inside, so pi to the cotangent of y times d dy of cotangent of y. Wait a second, make sure that's making sense to you. It's okay if it doesn't. We can work through it. Just need to chip away. Outer function is the pi function. It is the exponential pi. So the derivative of an exponential function is natural log of your base, so natural log of pi times pi to the x, but it's the derivative of the outside evaluated the inside. And so that's why it's pi to the cotangent y, then times the derivative of cotangent y, which I don't think you should have memorized yet. It's been a while. So the derivative of cotangent is negative cosecant squared. So this should be, this is negative cosecant squared of y. So at the end of the day, we have negative natural log of pi times pi to the cotangent of y times cosecant squared of y. I put the negative all the way at the front. Just because I like the look of it better. You could leave it as times parentheses negative cosecant squared. That would be fine too. It's not wrong. It's just, it looks prettier this way.
Just because like any negative product is just that they use all times negative one.
And so, and since this is all multiplied together, you can jumble it however you want. All right. Next one, natural log of 7x to the fifth minus 4e to the x cosine x. That's a chain rule because the outer function is natural log and the inside function is 7x to the fifth minus 4e to the x cosine x. But 4e to the x cosine x is a product. So we've got a product rule inside a chain rule. That can happen. So dy dx, or y prime, however you want to write it, is the derivative of the outside. The derivative of natural log is 1 over x, but this is natural log the derivative of natural log evaluated the inside. So it's 1 over 7x to the fifth minus 4e to the x cosine x times the derivative. So times d dx of 7x to the fifth minus 4e to the x cosine x. This is another reason why I like to do this version, because it allows me to take these as side steps. It allows me to take these derivatives separately, so I don't have to like try and figure it all out at once. But that's just how my brain works. So this one, derivative of 7x to the fifth is 35x to the fourth. But this one, product rule. So baby F. Oh, let's use green. This is baby F. And this is baby G. So baby F prime is 4e to the x. Baby G prime is negative sine of x. So this is going to be F prime, 4e to the x times G cosine x plus G prime. So negative sine of x times F, which is 4e to the x. Or preferably 4e to the x times cosine of x plus sine of x. Just to make it simpler to write, so we don't have to write as much. Okay. So, at the end of its glory, dy dx is f prime, so is the top, so that's 35x to the fourth, minus in parentheses 4e to the x times parentheses cosine of x plus sine of x, all divided by 7x to the fifth minus 4e to the x cosine of x. And you can simplify if you want, but since we're not being asked to do anything with this derivative, we'll just leave it as is.
Yes.
So then if we had to do a second order on that one, we would switch to a quotient rule.
Yes.
Okay.
If we had to do a second derivative, we would have to do a quotient rule, but inside the quotient rule, there'd be two product rules. It'd be pretty messy, but we could do it. You'll be a stronger mathematician for it. You'll be a stronger person. But we don't have to. Let's not do it. All right, this one, g of x equals e to the cosine of x cubed. Whenever you hear an of, that means it's going to be a chain rule, right? So that's e of cosine of. So that's two chain rules. G prime. Now, once you get good, you could do this. Derivative of the outside function. E is the outermost function. Derivative of E is itself. So this is e to the cosine of x cubed times the derivative of cosine of x cubed. The derivative, like outer function there is cosine. So it's going to be times negative sine of x cubed times the derivative of x cubed, which is 3x squared. So you can get to that point. If you feel comfortable doing that now, be my guest. But I'm going to show you I'm going to get all the work to do it though. I'm going to still do that for you because this is still tricky at first. G prime of x, outmost function is e. So it's going to be e to the cosine of x cubed times the derivative, ddx, of cosine of x cubed. Derivative of cosine of x cubed will be negative sine. So this will be e to the cosine of x cubed, that's still sticking around, times negative sine of x cubed times the derivative of the inside, ddx of x cubed, which is where I get my final answer. You can simplify it if you want to, but we don't need to. Yes, Jade.
Okay, so basically it's kind of just like, at least with this problem, just 3 steps.
Mhm.
You find the outermost, then you do
Inner, like the second inner.
inner. Okay,
Yes.
that
So
kind of connecting.
good. Yeah, I'll tell you one thing. So there's a problem, and I have it in my notes deliberately as an exercise. This problem right here. This was a question. So I don't do WebAssign or my lab or anything like that because I don't. There's some problems within calculus. By the way, when I was taking calculus, it was like one of the first times that these the online homework systems had been created. So I had it when it was in its infancy, and they've gotten a lot better over time. But one of the problems on our homework was to find the derivative of a function very similar to that, and that's a chain rule within a chain rule within that's a chain rule within a chain rule within a chain rule within a chain rule. If you can get that problem correctly, you understand the chain rule. If you can do that problem right, you got it. You got it down. The frustrating thing was trying to type that into WebAssign, which is now called, I think called Cengage, but like into MyLab, because imagine you make one small error, you accidentally do a multiplication sign instead of parentheses, or you misspell tangent, not speaking from experience or anything like that, and you get it all wrong. Very frustrating to do on a computer program. I became a tutor at University of Washington, and I had to see that problem over and over and over again. And like it got to the point where I was like, just give me it. Just give me it. I'm just going to do it for you. I was so done with that problem because it happened every semester or every quarter. But anyway, if you can do question number 4, you understand the chain rule, is what I'll tell you. These problems right here, they were trying to remind us of a little nifty thing. But I'll make a video on that one. We'll skip those for now. And we'll go straight to this problem right here. So just be on the lookout for a video or I'll fill it in for you later on. But this one, you can't see that it's to the 3rd power because it was hidden. So it's the 7th power. So yes, one thing to do if you really didn't want to use the chain rule is you could x squared plus 1 to the 7th power, FOIL that out, x cubed plus 2x minus 3 to the 7th power, FOIL that out, but who wants to do that? Instead, we'll do the chain rule. That's a function. That's that rational function that is raised to the 7th power. So f prime of x will be the 7th power. That's the outer function. So that's going to be 7 times the thing to the 6th power. That's the power rule in action. x squared plus 1 divided by x cubed plus 2x minus 3 times the derivative of x squared plus 1 over x cubed plus 2x minus 3. And that's going to be a quotient rule. That'll be your f. That'll be your g. So start your function on the very, very left here. 7 times x squared plus 1 over x cubed plus 2x minus 3 to the 6th power times f prime g minus g prime f all over g squared. And I'm going to memorize this one. Good. We're going to get it memorized soon enough. F prime is 2x. G prime is 3x squared plus 2. So f prime g, x cubed plus 2x minus 3, minus g prime, so 3x squared plus 2 in parentheses, times f, x squared plus 1, all divided by g squared. So x cubed plus 2x minus 3 squared. And that is our derivative. Beautiful. Now find where that equals 0.
Set that as the final answer right there.
Yeah. Don't simplify it. You burn your corneas trying to get it right. All right. This one, and then okay, so we're right on schedule. We caught up. Yay. If we have time at the end, we'll get those other ones. Otherwise, we'll make a video. This one, I'd like you guys to try this one yourselves. I'm just going to pause the recording and fill it in so that you're working. All right, I have the answer up here. I know I'm going quick. Don't assume I don't assume that you were able to get it that quickly. I've been doing this for a long time. So, and even still, I just love taking derivatives. They're so fun. It's like a little Sudoku. Just think of it that way. Make it easier. So don't worry if you're not going as fast as I am. It takes a lot of practice. Easily 10 years of it. So once again, so let's go through the problem. So that's a product of two functions. That's a product of e to the 4x squared and tangent of natural log of x. So for the first thing, you're going to need to do a chain rule. Derivative of the outside function, e, evaluated the inside function. So that's why you get e to the 4x squared times the derivative of the inside, which is 8x. Second one, tangent is the outside function, natural log is the inside. Derivative of the outside function, tangent is secant squared. So secant squared of ln of x times the derivative of natural log of x, which is 1 over x. So that's why you get that secant squared of natural log of x over x, and then fill it into the formula. F prime g plus g prime f. All right. Now, I have it on my calendar that we will have, like, we're going to finish up 2.4 on Wednesday. I want to do one additional example. I'm going to add this in here because this is very, very common mistake and I want to nip it in the bud. I need to add it to my notes. We're going to call it a bonus problem to make it sound fun. Bonus. Let's say f of x is equal to secant of, someone give me a function. X squared plus 4, love it. The question that I want to know is why? Why was that the first thing that came to your mind? No idea why.
Nice and easy.
All right, so classic mistake students will make, because the derivative of secant is secant of x tangent x, but we abbreviate it, we bastardize it and say secant tangent, and that's not what it is. So the derivative of secant of x is secant of x tangent of x. The derivative of secant of x squared plus 4 will be different. The derivative of secant x, so f prime of x. The outer function is secant. So the derivative of secant is secant of x tangent of x, but this a derivative of the outside function evaluated at the inside. So this will be secant of x squared plus 4 times tangent of x squared plus 4. Then times the derivative of x squared plus 4. Does everyone see that? That's an important one. It's not secant tangent, like it's not secant x tangent x times x derivative of x squared plus 4. It's secant of the inside times tangent of the inside. So at the end of the day, that should be 2x secant of x squared plus 4 times tangent of x squared plus 4. It's a classic mistake students make, and I don't want it to happen to you guys. Any questions on that? All right. And then can move on. Conceptual problems. Super fun one. Love it. You've got F, G, and H here. F is the dashed function, G is the blue function, and H is given a chart. So given all that information, find ddx of f of h of x, evaluated x equals 1. So when you're looking at this, there's no functions given. So we can't do the procedural method we've been doing before. We have to appeal straight to the definition. By definition, this is f prime of h of 1 times h prime of 1. Because ddx of f of g of x is f prime of g of x times g prime of x. So all I'm doing is I'm replacing the x's with 1s. F prime, I suppose I should have said f of h of x, but either way. F prime of h of 1 times h prime of 1. Adding a little bit of complexity here. Adding a little extra spice. Maybe some cayenne pepper. Maybe some. We don't like. I'd say this is a significant amount of spice. Maybe so. Cayenne pepper is probably a good choice. Doesn't like paprika or something, which doesn't do anything. And the specific, we could do something. Bay leaves. Bay leaves don't belong in the world. They're not useful. I've taken a bay leaf out of every recipe that's required a bay leaf, and I don't notice a difference at all. Maybe I'm not using the right bay leaves, but either way. Once again, by definition, the composite, the chain rule says that it's f prime of g of x times g prime of x. So in this case, it would be f prime of h of x times h prime of x. But we're evaluating it at x equals 1. So that's why it's f prime of h of 1 times h prime of 1. So h of 1. H is given a chart. And so the way we read this chart is it's saying h of x will equal 7 when x is equal to 3, and h of x will equal -1 when x is 1. So that's -1, and h prime of 1 is 3. So yeah. So what this is f prime of -1 times 3. And now we need to look at the graph to figure this out. F prime of -1. John Doe says that it's 0. Why is John Doe wrong? That's the function at 0. Sorry, the function at -1 is 0. But the derivative at -1 is the slope of the tangent line there. So slope equal to -1, right? It's down 1 over 1. Yeah, which implies that f prime of -1 is -1. So this equals -1. So the final answer is that this is equal to -3. Fun conceptual problem. Right. This one, we'll find the slope of the tangent. So we're trying to find the equation of the tangent line at x equals pi. Because why not? We can find the derivative at a weird value like pi. So let's find the slope, because we need to find a tangent line, we need a point, and we need the slope. So for the slope, k prime of x, by definition, would be g prime of sine of x times the derivative of sine of x. Or specifically, g prime of sine of x times cosine of x. So when you don't like, this is kind of a little trick to know about when it comes to conceptual problems in mathematics. If they don't give you an equation, treat it like just a generic function and appeal straight to the definition. We don't know what g is, we'll just call it g prime.
What do you say by definition, you mean of the chain?
For the chain rule, quotient rule, anything, whenever you're involving an arbitrary function, appeal straight to the definition.
But I mean, in this case, it's the definition of the chain.
Yes, in this case, it's the definition of the train rule, yes. So that's what k prime is. So k prime of pi would be g prime of sine of pi times cosine of pi. Sine of pi is 0. Good. So this is going to equal g prime of 0 times cosine of pi is, ooh, close. -1, -1. So now we need to know what g prime of 0 is. So we'll refer to the graph. G prime of 0 is the tangent line at 0, the slope of the tangent line at 0, which is 0. Slope equals 0, which implies that g prime of 0 is 0. So that's going to be 0 times -1, which is just 0. That's our MTAN. It's okay to have a 0 slope. That's fine. That's okay. That happens to us sometimes. Point. This is a point on K. So we know we want to find K of pi. K of pi is G of sine of pi, which is G of 0. And so what color haven't I used? Have I used blue? I've used or. Let's use blue. Yeah, let's use blue. G of 0, not G prime of 0, but G of 0 is the Y value there, which is 1. Yes, that equals 1. So that's going to be pi comma 1, a point. So y minus 1 is equal to m, which is 0 times x minus pi, or y is equal to 1. And this is the one time where I'm like, you know what, the secondary form of it might be better. And that'll do it for today. But any questions on that? We can always come back at the end tomorrow or on Wednesday. So as a reminder, we have a quiz on Wednesday. It'll cover a little bit of chain rule because I need, like, normally I wouldn't put that on the quiz right away, but because it's so important, I'm going to put chain rule problems on there. Not complicated ones like
Like not the crazy ones, but there will be a chain rule, at least one. Okay?
So the quiz is 2.2, 2.3, and a bit of 2.3.
Yes. But the thing is, with these sections, they all build on each other. You can't do 2.3 unless you know 2.2. You can't do 2.4 unless you know 2.3. So it all builds on it. If you guys have any questions, feel free to ask. Otherwise, I will see you guys on Wednesday. Please remember that your exam redo is due then. If you want to come to my office hours, they're tomorrow from 10 to 12:20. There's a link on my on the homepage, or other times if those don't fit for you. Okay. Otherwise, have a good day, and I'll see you Wednesday.